Hey everybody, I hope you're doing well. Today's screencast will be mainly about logarithms, which is section 4.3 in the book. But I'm going to start with just a couple of review examples involving exponential functions and compound interest. So let's start with the compound interest formula, which we introduced in the previous screencast. It's highlighted in blue on the screen now. And try one of the exercises from the notes and exercises. So 411, let's find that one. Is right here, right? So the idea here is you invest $500 or you have a $500 asset of some sort, and it grows according to some different scenarios. We're just going to do some different computations here. So let's say it grows at 6.2% compounded quarterly for 8 years. So all we have to do here is identify the pieces of the problem, right? A is the initial amount, so that's the $500. R is the nominal rate, that is the 6.2%. K is the number of compoundings per year. So in this case, we're compounding quarterly, so K is 4, and T is the number of years, which is here 8. So I just take all of those values, plunk them into the formula, right? So there are my A, R, K, and T values, and when I plug them in, hopefully that's the next cell, yes indeed. It looks like this. And I just load that into a calculator and it comes out to 817.95. So my $500 has grown to about $818. Again, be careful on your calculator. Either make sure that exponent is in parentheses or just do 8 times 4 is 32 and do the number 32. But keep your exponents in parentheses when you enter into a calculator. All right, that's pretty straightforward. Let's do maybe one more. Let's try, we'll just do the next one, I guess. 10.2% compounded monthly for 8 years. So notice I expect to make more money here. I'm making a significantly higher rate of return. And there's more compounding, which helps a little. The rate is a much more important factor than the compounding. In any event, in this case, let's see if we identify our A, R, K, and T values, right? A starting amount is 500. Notice that an interest rate of 10.2% is 0.102, not 10.2, right? The 10.2 is a percentage. So when you convert that to a number, make sure you slide the decimal over. Likewise, 6.2% is 0.062. Monthly compounding is 12 compoundings per year, and the time passing by is still 8 years. So let's go ahead again. I load that all into the formula, put it in a calculator, and indeed I do better here. Right now, my asset's worth more than $1,100. Last time I was worth about $818. Okay, good enough. There are the two parts here are pretty similar. I'll leave those for you to look at. Let's do an example involving effective annual rates, and then I think we can move on maybe to logarithms. Let's see, is that the plan? Yeah, maybe we'll do one more. Okay, in any event, let's do this. Let's pull this up a little so we can see the problem below it, right? Okay, so I want to know, we can just focus on the question here, what's the effective annual rate of 4% compounded monthly? So the trick that I introduced in the previous screencast is to take $100 and invest it in the scheme for 1 year and see what happens, right? So if I do that, then my initial amount is 100, the rate is 0.04, right, 4%. Compounding is monthly, right? So that's where the 12 comes from. And I'm investing for 1 year. So I just have 12 times 1 in the exponent. I do the calculation. I come out with this and I can see the effective rate, right? 100 to 104.07. This is why I start with $100. So I can easily see what the percent change was. It's 4.07%. And again, we see that compounding has the effect of slightly increasing the rate of return. So your actual rate of return or effective rate of return is a little bigger than the nominal rate of return. Similarly, for the next one there, the effective annual rate of 12% compounded daily, same idea, invest $100 in this scheme, there's the 100, 0.12, that's the rate, right, that's the 12%. Daily compounding means 365 times per year. I have a ×1 in the exponent there that I don't really need to write. Do it on my calculator and I can see that my money grew by 12.75%. So again, we get a a slightly larger rate than the nominal rate because of the effect of the compounding. Let's see what 4.14 was. Sure. So we can talk about this one a little bit too. We talked. I will talk more about modeling with exponential and logarithmic functions in the next section. I think it's section 4.4 that we'll talk about next week. But we've done a little bit of modeling in the previous screencast, and one scenario we considered was the decay of a radioactive substance, right? So various chemicals exhibit this phenomena. Suppose the substance decays at a continuous rate of 14% per year, and 50 grams are present in the year 2000. I want a formula for the amount of substance T years after the year 2000, right? I'm looking at this right here. Okay, well, this is something that we can almost write down right off the bat. I'm going to use the continuous growth form of our exponential model because in the problem, you can see the bold-faced text, I'm given the continuous rate of decay. And so the continuous growth form is this base E exponential. We talked about the number E in the previous screencast. 50 is the initial amount. And what this measures, of course, is the number of grams of the substance T years after 2000. Okay, and so if I want to know how much substance will be there in the year 2012, that's T equals 12, right? It's T years after 2000. It's important to be able to interpret your variables appropriately, right? So to translate what things in the problem corresponding to what variable value. So when I plug in T equals 12 to my formula, and I just do that on a calculator, I come out with 9.319. So in 12 years, there's, it's shrunk quite a bit, right, to less than 1/5 of its original size. And we noted last time that we can go from continuous growth form to per time unit growth form fairly easily. I just use properties of exponentials to say that e to the minus 0.14t is e to the minus 0.14 raised to the t power, because when you do a power to a power, you multiply the exponents. And now I can just do this thing on my calculator. I just type in e to the minus 0.14. My calculator says that's 0.869. And here I have per time unit growth, right? So I can see that per time unit, it's decaying by about 13%. All right, so that's all review. Let's start into some new stuff now and talk about logarithmic functions. All right, so first of all, this function, right? So this is, we introduced last time exponential models, which had the form a times b to the t. If you throw the a part out and you just look at the function y equals b to the input, we'll call this the exponential function base b. And we insist here that b is a positive number. We've never used negative bases in our exponentials, and we won't going forward. Okay, so a little bit of terminology is all that is. We are going to define a new function called the logarithm base b, and we're going to write it like that highlighted blue thing. So we'll shorten logarithm to log, L-O-G, and we'll write the b in a subscript. Notice that this is a function name. This blue thing is not multiplication. It's the log base b of x, not times x. All right, well, we have to say what this means. How do you compute this, this function? And what this means, if y is equal to log base b of x, is that b to the y power is equal to x. So you can think of this as kind of starting from the base here and making a little loop over to the right-hand side and circling back to the x, right? B to the y is equal to x. So let's look at a few examples that will start to clarify this a little bit. Well, first, a technical note. Exponentials are always positive. That is, if you take a positive number b, raise it to any power you want, positive power, negative power, 0, doesn't matter. The result will always be positive. So that means this x is always going to be a positive number, and that's the only thing I can plug into a logarithm. Logarithms have a restricted domain, right? So another way to say this is that the domain of this function, copy and paste, is the interval from 0 to infinity. Right? It's only, you can only take the logarithm of a positive number. If you try to take the logarithm of a negative number on your calculator, you'll either get an error or a complex number, and complex numbers are out of bounds for this course. Okay, so this question, when I'm taking the log base b of something, and I'll try to keep using parentheses there. That's not necessary, but it does make it look a little better. How do I figure out what y is? Well, the number y that's equal to the log base b of x is such that b to the y is equal to x. So to figure out y, I need to figure out what power do I have to raise b to get x? That is, b to what power equals x is a good way to think about what this logarithm is trying to do. So with that understanding, there are some examples that we can figure out. Another technical point, generally speaking, we'll have a base on the logarithm, but two important logarithms are the log base 10, and for the log base 10, we'll drop the base altogether and write log. And the other one that is important is the log base e, where e again is Euler's number. We'll write that ln instead of log. Ln is an abbreviation of logarithm naturel, which is the French for natural logarithm. And indeed, the name of this function is the natural logarithm. Log is sometimes called the common logarithm. In any event, these are two important logarithms. You should have buttons on your calculator for both of these, ln and log. More about that later. I think we finally are getting to the point, yes, where we can do some examples to try to dispel some of the fog around logarithms here. Okay, first of all, 2 cubed is 8. Well, that's not super mysterious, but I can rewrite this as a logarithmic equation, right? If 2 to the power of 3 is 8, it means the log base 2 of 8 is 3. Because when I take the log base 2 of 8, I'm asking 2 to what power is 8? Well, the answer is 3, right? Because 2 to the 3 is 8. Again, let's put parentheses in there. So here we've computed our first logarithm. And basically any power equation like this, you can convert into a logarithmic equation. Logs and powers kind of go in opposite directions. If 2 to the 3 is equal to 8, so the sort of the exponential base 2 maps 3 to 8, the logarithm base 2 is the inverse. It maps 8 back to 3, right? They go in reverse directions. Let's do a few more examples. Here's another exponential equation, right? 9 squared is 81. That means 9 to the 2 power is equal to 81. So when I take the log base 9 of 81, I'm asking, what do I raise 9 to get 81? Well, the answer is 2. So the log base 9 of 81 is 2. More examples. What is the log base 3 of 27, right? So suppose we're looking at this and we didn't see the answer here. I'm asking myself, what power do I have to raise 3 to get 27? Well, 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27. So there's my answer. You will notice that we can only compute logarithms like this in pretty special cases, right? If I asked you what the log base 2 of 4 is, hopefully you'd say 2, because 2 to the 2 is 4. But if I asked you what the log base 2 of 5 is, you'd kind of be stuck, right? There's not a nice power of 2 that gives 5. A note here on negative exponents and such, recall that the number 0.001 is 1 over 1,000th, which is 1 over 10 cubed, which is 10 to the minus 3 power. So if I want to take the logarithm, now notice in this logarithm here, keep inserting these parentheses, there's no subscript on the logarithm, which means it's log base 10, right? When you don't see a subscript, it's log base 10. So when I'm trying to compute this, again, let's ignore the right-hand side for the moment. I'm asking 10 to what power gives 0.001, and we have our answer right here, 10 to the minus 3 power. Okay, so the value of a logarithm can be negative. You just can't plug in a negative number to a logarithm. All right, moving right along. What is the log of 10? Again, I don't have any subscripts, so this is the log base 10, and I'm asking 10 to what power is 10? And the answer is 10 to the 1 is 10. What about the natural log of e to the 4th? Again, when I see ln, I'm thinking, okay, that's log base e. So this is asking e to what power is e to the 4? Well, e to the 4 is e to the 4. So there you go. Another example, how do I take the natural log of, say, 1 over e squared? Well, I'm asking e to what power is 1 over e squared? It's helpful to rewrite. Remember, 1 over e squared is e to the minus 2 power. And here I'm asking in this middle expression, e to what power is e to the negative 2? And the answer is negative 2. Here you get a real sense, hopefully in these last two examples, that the natural logarithm and the exponential base e are inverses, right? If you first apply exponential of 4 and then take the natural logarithm, you just get back to 4. And the same happens here with the input negative 2. Okay, a couple of other minor notes. First of all, anything to the 0 is 1 by definition. So if you take the logarithm of 1, doesn't matter what the base is, you're asking b to what power is 1, and the answer is b to the 0 power is 1. So the logarithm of 1 is always equal to 0, regardless of the base. It's true for the common log and the natural log as well. Also, and we saw a couple examples of this actually right here, and again, really here and here, that if you take the log base b of b to the x, this is asking again, b to what power gives b to the x? And it's sort of a tautology, right? B to the x power gives b to the x power. So the answer here should be x. And here again, we see an illustration of how if you compose the exponential base b with the logarithm base b, they're inverse functions, which means they kind of wipe each other out and you get back to the x. And here are two specific examples of this, right? So if this b is the number e, then the log base b is ln. And so the natural log of e to anything is the anything. Again, this equation here is just a special case of this equation with b equals e. And this equation is the special case with b equals 10, right? So if the base is 10, then we just write log with no subscript. And then I get the log of 10 to the a is equal to a. So logarithms and exponentials undo each other. This is a very useful property for us when it comes to working with exponential models. A real quick word about graphs. Here is the graph of the log base 2 of x. And this basic shape is what a logarithm, the graph of a log, looks like. So this is the function y equals log base 2 of x. Notice that the graph sort of is all to the right of 0 because the domain is only positive numbers. There is no graph over for negative input values. As I increase the base, I kind of flatten the curve. See how that curve is going down and flattening out. As I decrease the base, the reverse happens, right? So a lower base is sort of a more sharply increasing function, and a higher base is a flatter function. Notice also they all go through this point where the cursor is. That's the point 1, 0, and that's because the logarithm of 1 is always 0, regardless of what the base is. Okay, let's look at a quick exercise and then solve some exponential equations. Actually, you know what? I'm going to jump over this exercise for now because we just did a lot of that and just talk about solving some exponential equations, which is our first and a very important property of logarithms. So before we get there, a word about computing logarithms. We computed some logarithms above, but if I ask you for like the log base 10 of 37, so that's asking 10 to what power is 37. You can't do that in your head, but you can do it on a calculator. because you should have an LOG button on your calculator. Google Calculator certainly does, as well as an LN button, right? So if I want to calculate, for example, the log of 453, I go to Google Calculator and it tells me that 10 to the 2.656 power is about 453. Okay, that's lovely. And here's a natural logarithm done on a calculator. How the calculator does that is beyond our scope, but we'll trust that it's getting the right values. But it does beg a question. Well, before we get to that question, actually, let's see then how we can use this information to solve an equation like this. So notice the variable here is up in the exponent. In order to solve this equation, I want to get that variable by itself, which means I somehow have to wipe out this exponential function or get rid of that exponential function. We now know that the natural logarithm is the inverse of the exponential base e. So what I will do is take the natural log of both sides, right? You can do anything to both sides of an equation as long as you do it the exact same way on both sides. So I take the natural log on the left and I take the natural log on the right. And this works because as we saw above, the natural log of e to anything is the anything. So on the left, I just get x. And on the right, I get something I can do on my calculator. And I come out with x is 2.879 as the solution to that equation. Okay, a similar example, I think, here, right? So again, I have an exponential equation I want to solve. The variable is right there in the exponent. So once again, what I'm going to do is apply the natural logarithm to get rid of that exponential. So I'm going to take the same first step here, take the natural log of both sides, parentheses in. Again, the parentheses aren't essential, but I think they are a little clearer. It's a little nicer with them than without them, right? So I take the natural log on the left, I take the natural log on the right. On the left, I have the natural log of e to something. Those are inverses, they undo each other. The natural log of e to anything is the anything. So on the left, I just get the 0.04x right here, right? So that's a lot better than it was before. And on the right, I get this thing that I can do on my calculator, the natural log of 900. My next step from here, of course, I just have a number multiplying the x on the right. So I just divide both sides by 0.04 and I get this. In general, when you're solving equations and there's going to be calculator work, best practice is to leave it all for the end and do the whole computation all in one go, rather than doing this, the ln of 900 halfway through. Save it for the end and dump the whole thing into a calculator to minimize round off error. And my calculator tells me this comes out to be 170.06. Let's maybe we can get Google Calculator up here. So yeah, what did I want to do again? Natural log of 100 divided by 900 divided by 0.04. So here's the LN button and here's the LOG button on Google Calculator, right? So I do that, 900, close the parentheses, divided by, whoops, divided by 0.04. Right, and there's the 170 that we got. Okay, so let's keep going with some equation solving here. Here's another example, right? So these equations were sort of building up and getting steadily more complicated. Be careful with this one. In the previous two, the thing we did was right away we took the natural log of both sides. That's not the best strategy here. And the reason is the left side isn't just purely an exponential. I've got this constant 230 that's kind of in the way. So what I'm going to do first is get that constant out of there. First, I'm going to divide both sides by 230. So when I do that, the 230 cancels on the left. Right, so here's the initial equation. When I divide both sides by 230, it goes away on the left, and on the right, I get this 1500 divided by 230. Now, best practice would actually not be to do this on a calculator until the end. But it's, you know, it's not a huge crime to do that along the way. You'll just get a little bit more round off error. And now, of course, the important thing is now I have an equation here that's just like the previous example, right? I've got an exponential equal to a number. So now I can take the natural log on both sides. Indeed, let's do that, see what happens. right? So here's the original. I take the natural log on the left. We've seen this a couple times now. When I take the natural log of the exponential, I just get the 0.07x. On the right, I get the natural log of that number. And then I divide both sides by 0.07. And so I get here, let's slow down a little bit. A little arrow, boom. I get x equals ln of 6.522 divided by 0.07, right? And that comes out to be, oh, and I deleted the number, didn't I? So I'll have to do that again. Let's clear this. Ln 6.522 divided by 0.07. There, 26.78. Okay, great. So one more example, I think, like this. What about this equation? So notice here in the previous examples, the exponential base was always e. Now I have an equation with an exponential base of 10. I'm not going to take the natural log on both sides because the natural log is not the inverse of the exponential base 10. Rather, I'm going to go ahead and take the common log, log of both sides. And when I do that, right, on the left, I get log of 10 to that 0.23x, and on the right, I get a log of 900. And on the left, the log of 10 to something is the something. So I just get the 0.23, where is it, 0.23x, there you are, right, on the left-hand side. And on the right, I get something that I can do on my calculator. Now, again, best practice, and I'm sort of contradicting my best practice, is actually to leave that calculation to the end. So let's do that. Let's just leave that as the log of 900. Now I will, here I'm just have an x multiplied by 0.23 on both sides. So I'm going to go ahead and divide both sides by 0.23. Right, so here's my, so let's get rid of this and see what we get. We're going to get log of 900 divided by 0.23, and we'll go to the calculator to see what that is. So let's see, let's clear this. Log 900 divided by 0.23, 12.845. There we go. All right, let's see a couple more quick things here. A key property of logarithms that's going to help us in solving some of these equations. If we take this, this far left thing that looks like a bit of a mess, what I want to focus on is in the exponent here, I have two factors, a capital B and then this log base B. So I have an exponent that's a product, which means I'm really doing a power to a power, right? Because when you raise a power to a power, you multiply the exponents. So in order to simplify that blue thing, I should do B times log base BA in the exponent, which is exactly what I was doing over here. Now we saw up above that B and log base B are inverses. So if you do B to the log base B, they wipe each other out and that whole blue thing just becomes an A. So this is just equal to A to the B. Consequence of this is that if you take the log base B of A to the B, you are asking B to little b to what power is A to the capital B? And the answer is this thing, is whoops, this exponent right here, right? B to that power is equal to A to the B. It's not a huge deal if you understand this justification, but I just wanted to give some justification for this red formula, which is the important thing here. This is often read, the log of a power is the power times the log, right? On the left-hand side, I have the log of a power. On the right-hand side, I have a power times the log. Why are we sort of plopping this down here? What's the point of these shenanigans with the A's and B's? This is actually very useful for a variety of reasons. Here's first one application. Suppose I want to compute the log base 4 of 87. Well, on my calculator, I don't have a log base 4 button. On your calculator, buried in the catalog or something, you may have a way to do logs of other bases, but the fact is we don't actually need all of these logarithms, and here's why. if y is the log base 4 of 87, so just basically give this a variable name, then I can write that as an exponential equation, right? It means 4 to the y is the 87 power. And I can solve this equation by taking the natural log of both sides. Now that doesn't look right, Because this is not an exponential base e, but bear with me, let's take the ln of both sides and see what happens. Right, so here's the initial equation, 4 to the y equals 87. Then I take the natural log of both sides, and I'm going to get ln of 4 to the y on the left, and I'm going to get the ln of 87 on the right. Now, here, ln and exponential base 4 are not inverses, so that's not just equal to y. However, the log of a power is the power times the log. So this y can come down front, right there. That's the power times the log. And that's a really useful step. Let's put a little arrow in here. Because in this equation right here, the y is not in the exponent anymore, which makes things a lot simpler. That blue equation is just y multiplied by a number is equal to another number. So I'll divide both sides by the ln of 4. I get this, and now I have something that I can do on my calculator, right? The initial thing I couldn't do because I don't have an easily accessible log base 4 button, but I do have an ln button. So I can do that blue thing, and when I do it on the calculator, I come out with 3.221. So the upshot of this is if you want to take any logarithm, log base b of x, and you can see this here, right? In this example, b was 4 and x was 87. What does it come out to be? The natural log of the x divided by the natural log of the b. And in this way, you can compute any logarithm you want just using natural logarithms, which is nice because the ln button is right there on the front of the calculator. Whoops. So for example, if I want to compute the log base 5 of 782, so this is asking 5 to what power is 782? I don't know, but I can do this simplification here, right? It's the natural log of 782 divided by the natural log of 5. Everything there can easily be done on the calculator. I come out with 4.139. Okay. So let's try to solve probably the hardest exponential equation we have seen yet today, this one right here. Now, the variable is right there. It only occurs once in the entire equation in that exponent. And what I want to do is do things to both sides that sort of get that variable as by itself as possible. Well, the first thing I'm going to do is get rid of this 14, right? That'll make things a little simpler. So I'll divide both sides by 14. Again, I want to kind of get stuff away from the variable, right? So that's just the initial equation. I haven't done anything yet. Then I will divide both sides by 14. So when I do that, right, the 14 goes away on the left-hand side, and I just get 1.05t. And on the right, I get 800 over 14. You can do that on the fly on a calculator if you want, or you can just leave it as 800 over 14. All right, so how do I solve this equation? Well, what I'm going to do is the same strategy we employed up here in solving this equation, and that is to take the natural log on both sides and not worry about a base mismatch, right? So that is, this is not e to the t, it's 1.05 to the t, but I don't care. I'm going to take the natural log on both sides anyway. It's certainly legal as long as you do it on both sides, right? So I get the natural log of 1.05 to the t on the left. I get the natural log of 800 over 14 on the right. And now the reason this works is this left-hand side is the log of a power, and the log of a power is the power times the log. So that t falls down front, right? Here is the power times the log, t times ln of 1.05. The right-hand side is the same. And now this blue thing is just t times a number. So all I do is divide both sides by the number, and I get t by itself, right? So t is equal to the log of 800 over 14 was what was there before, divided by the log of 1.05. Pile all that into a calculator, and you get 82.917. Notice that we can interpret this in terms of exponential models. This right here is an exponential growth model that models something with an initial quantity of 14, right? That's the initial quantity that grows by 5% per time period, right? 1.05 is the base. And we're sort of asking here, what time will make that quantity equal to 800, right? So it starts at 14, it grows 5% every year. And what we have found is that it takes about 83 years for it to grow to be 800, 82.9 years, 917 years to be precise. Okay, so again, practice, practice, practice. I will open up these exercise solutions when I post the notes so that you can see those. Again, these numbers refer to the corresponding numbers in the notes and exercises. So there's lots of practice in the book and in the notes. Please do as much as you can. The quiz is on 4.1 and